solar system, I think. It's the only man-made object to leave the solar system, right? Likely the only one to ever do it ever again. Who knows? Okay. Now, 2 questions about a great big NASA rocket. Question number 1, how do you keep it from tipping over? Rockets would seem to be, on the outset, tall, tippy things. And if you look at the German footage of them trying to design rockets, many of them went boom, yeah? Oops. Have you ever seen those the footage of them testing the liquid fuel rockets? Yeah. So why doesn't that rocket tip over? It's not because it's perfectly balanced. There are things like gusts of wind that might knock it over. Do we know? Let me give you a clue. Have you seen the movie Apollo 13? Yes. As the rocket is going by, the shot is like this. You're looking at it through the gantry window. The rocket is going past the window. You remember that shot? Yes. As it goes by, when I saw the movie, I heard all these sounds. I heard a sounds like as it goes by, like little thrusters. There's little thrusters all up and down the body of the rocket. Do you see them on here? They're not really on here, are they? Okay. But there are little thrusters all up and down the body. Do you suppose that these great big rockets have computers on board? Do you suppose they have gyroscopes that can tell which way they're pointed? Do you suppose if they're ever not pointed the direction that they're supposed to be, that there's little mini thrusters on the side, little things that go and adjust the exact angle of the rocket? Do you think so? Yeah, I'm thinking so. These rockets are, for the Saturn V rocket, okay, they actually light the engines 8.49 seconds before it's supposed to lift off, yes? Okay, then it sits there and it's got a little computer probe there, and it confirms that the thing is actually trying to lift off. Okay, as soon as it confirms that it's actually pulling up, it lets go of the rocket, yeah, and the rocket starts to take off. As it takes off, it's got these things, it's got to actually pull these things through a metal channel. It's like a resistance thing, okay? So it actually pulls it through a metal channel for a while, and then it's free to go. As soon as it's free of those clamps on the bottom, because the problem was, if the engine's partly ignited, there was no easy way for it to resettle back down onto the launch pad without going boom, yeah? Right? So they had to make sure it was a go before they let go of it, right? So as soon as it let go, the thing tilted 1.5 degrees away from the gantry tower to avoid running into it, like the wind might blow it into it, right? Then it went and then, as soon as it was up in the air, it had an exact calculation of exactly what the angle should be at every elevation so that it optimally entered orbit, yeah? So it's not like it's an accident. This thing is flying exactly at the angle that it's programmed to by computers, running on discrete transistors. Do you know what I'm saying? Transistors this big are in this thing, and they are making the computer that runs that. Okay, the computers in this room have millions and millions of transistors, all smaller than you can see with a microscope just about, right? Running it. This thing ran with individual transistors this big. They had not yet made chips yet. Yeah? Isn't that amazing? This is an amazing thing. Integrated circuits had not yet been made. Okay? Okay, second question. What is the steam coming off of these rockets? You always see this on the launch pad. It's ice. Why is there ice coming off the side? Because liquid oxygen that they put in these things, and in the shuttle rockets, liquid hydrogen as well, right? These are cryogenic gases. They're very, very cold gases. That's why they have to be loaded in right before launch, okay? Because they start to boil off right away. So you've got to use them up really fast. So that's what the ice and stuff coming off of that is. This was one of the shuttle, the Columbia, if you were following and reading the newspaper, okay? The Columbia failure was that the insulation on that tank full of hydrogen, these cryogenic gases, a chunk of the insulation fell off and hit the leading edge of one of these wings, I can't remember which one, damaged the tile enough that as it re-entered the atmosphere, the hot atmosphere got into that little crack and just...
Wait, was that the one that crashed like in Texas?
Yeah, kind of Texas and Louisiana and, across...
I heard like, that's crazy. The last thing that they heard from like the transmission was, oh no.
Yeah. That'd be bad. And here's a really very sad thing. The very sad thing was, had they been aware of this, had they been aware that the heat tiles had been damaged, they could have just gone to the space station, waited it out, and we could have rescued them with another space shuttle, fixed that space shuttle, et cetera, et cetera. We could have done that if we'd known. We just didn't know that that could have happened. From then to the very last shuttle launch, which just happened, is that right? Okay. They've now got this procedure where they go out and they do a spacewalk and they look at all the tiles. I don't know if they could spot a tile that's going to go bad, but they, Are they going to? I think so. Yeah. Now the very sad thing was that after the Challenger, the first one that went boom, Richard Feynman, a Nobel physicist, looked at the thing and just guessed that the failure rate would be about 2 in 100. Yeah. We've had about 108 shuttle missions. We had 108 when Columbia went off, and then we had 2 failures, right? So people say you can't predict the failure rate, but he did. So that's kind of okay. So let's do a little math, right? If we rearrange that formula and divide both sides by t, then we end up with this thing. And I think you guys wrote this down in your notes, but write it down if you haven't. Right, so F is, basically it's just F equals m dot delta V, right? M dot is equal to burn of mass divided by time, right? Okay. And then this is our exhaust gas velocity. You can make a little triangle with this. Yeah, where this is the fuel burn rate. And this is just a calculus notation, by the way. Something with a dot means the rate at which something changes. Okay, this is mass of fuel. This is kilograms, right? This is time in seconds, the time it takes to burn that. This is kilograms per second. And then you can, yeah. I mean, this one way to do it, right?
Is that M over T?
Yeah. So here's another formula for you if you want. You don't need to, but you can. You can. What's the next thing? Oh, there we go. So I'm lazy and I will write little m dot as burn rate, but really it's just the burn rate. So it's how many kilograms of fuel that you burn in a second. Anybody guess what this guy burns in a second? 2 kilograms a second. A touch higher than that. 3. Did somebody say 15,000? Yeah, that's exactly right. That's amazing. How do you guys know that? It's 15 tons of fuel, more metric tons of fuel, right? A second. This is an amazing amount of fuel. All right, so a rocket burns 1,500 kilograms of fuel in 12 seconds. What's its fuel burn rate? Well, that's going to be 1,500 kilograms, right? Divided by 12 seconds. What is that? Yeah, you guys are just such smart, Alex. 125. Yeah? That's not hard. Is that hard? No. You guys want to try this? Wake up your neighbor. Have them try this. Whiteboard, whiteboard.
When's the best time to have a bathroom?
Right now. Does anybody need a whiteboard?
Make sure this is a whiteboard. My mom said it was.